Hi everyone, thank you so much for joining us today. We have with us Dr. Randall Balestriero. He is an assistant professor at Brown University, and he has been doing research in learnable signal processing since 2013. In 2016, he joined Rice University for PhD, and he has done his postdoc with Meta AI with Dr. Jan LeCun. Today, he will be talking about his latest research paper, The Fair Language Model Paradox. Thank you so much for joining us today, and I'll pass it over to you.
Great, thanks. First, thanks for the invitation. And by the way, thanks for Cohere and Cohere for AI for all those open science initiatives. That's really helpful, especially in the LLM sphere, so that's pretty nice. And today I will present recent work we've been doing with a couple of other people. So Andrea, we just did his master's from MIT with Tommaso Poggio, and Tomer, who just joined Texas A&M as a new faculty. So I will put their email at the end of the slide deck, but yeah, definitely reach out to us if you have any question or ideas for collaboration. So today we're going to focus specifically on large language model. And I'm pretty sure if you are here, you are already convinced that they are really at the center of current industrial revolution. They are really central to many different types of products. And just to really illustrate this, this is a schema I took from the Cohere website. So you can see, for example, that you can use those large language model. So you can just think of them as gigantic networks that can digest text inputs. And then you can use that either to generate new text, answer questions, or do a bit more in-depth analysis. So for example, you can try to use that to analyze data that you might have or that your business might have. So this is a type of example you see on the left. You can try to use those language models to condition other generative networks like image generation, which is what you see in the middle. So again, a lot of application for art and content creation in general. And then you can see on the right also other applications where you could try to interact with your apps, or you could try to generate code to create new apps. So there is really no clear limit, at least as of today, as to what LLMs can really do in the real world. And so this is really central to a lot of companies. And so those LLMs are really the center of the technology. And because of this, there is a huge rush to get them into production, train bigger and bigger ones, and a lot of, let's say, scientific steps to trying to understand what really happens inside them have been short circuit because of this rush. And that's really what we try to focus on in this work. So let's give a bit more of a practical picture first. So if you are trying to use or develop a LLM for your specific product or application, it will usually look like this. So of course, you can imagine, because of the diversity of possible application, a single image cannot summarize everything, but roughly you have those key moving components always present. The first one is what you see in green on the left, which is a pre-training phase. So during this pre-training, you start from designing a model and architecture, which usually is defined as how many attention layers you want, basically how many heads, how many parameters, etc. So a really high-level design of the structure of the LLM. And this starts from random weights. It's a randomly initialized model. So as it is at this point, it's pretty much useless. So the goal is to go from this random initialization to a better than random set of parameters that then will make the life of the users easier through very short fine-tuning, supervised fine-tuning, or RLHF. So this pre-training phase, concretely, you use a gigantic text corpus. So for example, here you see a couple examples from Wikipedia articles, but pretty much everything you can, let's say, legally find on the web. And in this task, you will first transform that corpus into a token. So this is just an alternative representation of the raw characters. You can really think of this as a lossless compression, and we will dive into those details a little bit more later. But just think of this as a pre-processing of your text. And then you will pre-train your randomly initialized language model through basically autoregressive classification task, which is next token prediction. So it's a really general and simple setting of given past token. So for example, the first half of a sentence, can you predict what will be the next token that comes after it? So it's a language modeling, generative type of pre-training. Of course, a lot of different variants exist. This is probably the one that is the most used today. Before that, you had things closer to BERT style pre-training, where you were trying to figure out which sentences are close to each other. But those type of models don't have generative capabilities out of the box. So that's why now it's mostly in terms of this autoregressive classification task. And then once you are done with this pre-training phase, you obtain this pre-trained model, which has, hopefully, if everything went well, better than random parameters. And still, it's a very, very general model. So it's not going to be very good at a very, very specific task, but it has understood some underlying logic and generative laws about the language that then you can fine-tune to your task more specifically. And this is obviously a much simpler task than starting from random weights. So that's really the goal of pre-training, is to give a good starting point for any user or any application down the line. And then you can do fine-tuning, you can do RLHF. Honestly, what you can do after you do pre-training keeps expanding pretty much every day as people discover more and more applications of LLM. So this becomes more of uncharted territory in general. But pre-training is really the core thing that governs pretty much all of the models nowadays. And this is actually nice because this is what our study actually focuses on, is to try to understand a bit more precisely what happened during this pre-training phase. And this is really crucial because, again, what you produce through this pre-training is what all of the users will use downstream through fine-tuning. So we need to be really careful about what type of model we provide to people at the end of the pre-training. So let's go a little bit more in depth into what happens. And again, if you are very familiar with LLMs, this will just feel like a breeze for you, but it's nice to have a clear setup for our study. So the first part, as I mentioned just before, is this tokenization step. So there are many different ways to do tokenization. In this study, we use this byte pair encoding, but you have different variants. All of them rely on the same core principle, so you can just think of this as a general tokenizer. So first, of course, you have to train or learn that tokenizer. This involves a few steps, which again can vary, but in general, you have first a cleanup step where maybe you want to remove some very odd characters. So it could be maybe removing some accents or try to do some normalization. Very, very soft cleaning of the raw text that you got from the internet or some database. And then you want to decompose this gigantic corpus into words, which is this pre-tokenization phase. And again, this can vary depending on which tokenizer or which implementation you use. And then from that, you will first build a base vocabulary, which at the beginning are just going to be the unique characters after you do this normalization step that are present in the corpus. So you start from a very, very small vocabulary. In practice, could be in the order of 200 or 300. And this is the first step in the training of the tokenizer. And then what happens is that you will slowly, incrementally learn merge rules based on the most frequent pairs of current vocabulary you have in your tokenizer. And you will merge those into a new word in your vocabulary, basically a new token. So by doing that repeatedly, you will be able to update your vocabulary, add this new token to it, and then you update the representation of the words to keep this process going. So in the end, you repeat those last few steps until you build a vocabulary size that you define a priori. So just to give you a rough idea, the size of the vocabulary has been increasing more and more. Most of the models now use at least 60,000, but it can go way beyond that, like 120K and even more. So you really have to think of this vocabulary size as a sort of new alternative representation of the raw text, which is a lossless compression. This mapping from text to tokens is invertible. And this is a new space where you will do your next token prediction for your LLM. So this is how you train the tokenizer. And then, of course, in practice, because your LLM works in token space, you also need to be able to do inference with it. So given a new text or a new sentence, you need to first tokenize it to then process it in your LLM. But this is very simple and quick. You just reapply your same normalization, your merge rule, and you produce your tokens, basically. Then you have some details which are not really relevant for here, but just for completeness, you can add some special token to signal like the end of the sentence, beginning of the sentence, or anything else that you want your LLM to be aware of. And also, depending on the tokenizer, you may have some special token for things that you did not see during training of the tokenizer, basically. But yeah, those are less relevant for what we will speak. The key thing, though, is that, as you saw from this construction, there are a few things that the user has to define, like the vocabulary size, which define the type of data distribution that your LLM will work with. So if you change the vocabulary size or you change the way the tokenizer is built, so the way you find those merge rules, it will really change the distribution of tokens, which is the distribution that you try to learn to predict with your LLM. So to make this more concrete, here is a very simple example with the IMDb dataset. So it's a dataset of prompt with movie reviews. You see you have access to the user defined review on the left here, and then you have associated to it a label, which is basically the sentiment of the review. So for now, let's not worry about this. We only care about the text part. So this is a relatively small data set, around 50,000 prompts in total, but this is still quite representative of the English language. So if we take this corpus and then we train a tokenizer on it, then we will obtain this type of token distribution. So you see here it was with 30,000 tokens in total, but the type of heavy tail distribution you learn is pretty much the same, and it becomes worse and worse if you increase the number of the size of the vocabulary. But what you see is that a few tokens are going to represent the majority of your data. And then you have a huge amount of tokens that are going to be present only a small amount of time. So you have this really non-uniform distribution of token representation in your dataset. And this you can vary it based on the tokenizer, vocabulary size, and the merge rule. But this is what things will look like in an actual practical scenario. So this is what you do as a first step to build the dataset to work on. And then to do this actual pre-training phase, which again here we look as a decoder-only setting. You can have different variants. So the first step is tokenize the text corpus, so this left part that we just saw. And then you will process those tokens as input of the language model. And the target for it is to predict what is the next token coming after the currently observed sequence. So you can just define those targets as taking the original input token and shifting them forward, basically. So in practice, most of the time you just do a one-step prediction, but there have been some recent studies trying to do multi-step prediction as well. But here we will just focus on one step, although most of the findings should be the same in this other setting. And then you can do some extra implementation things. So for example, you may want the self-attention in the model to be causal. So this is one thing you can impose during the forward pass, but those are more implementation detail. And then given the target that you define from the tokens and the prediction of your LLM, you will compare them with the usual cross-entropy loss because since those things are discrete, you just consider it as a classification problem, basically. And then you repeat this process on all your prompts and you repeat this many epochs, possibly, until you converge or you have some stopping criteria that will produce your pre-trained model. So this is really, really generic and sort of a universal recipe nowadays to learn to pre-train a LLM. And then for inference, there are many different things depending on your application, but basically it will still involve tokenizing your inputs and then doing this next token generation, and you have different ways of sampling what the next token will be. And this is not so relevant, but you still work in token space, which is the key. And for us specifically, what will be very interesting is the fact that you compare the predicted tokens to the target with the cross-entropy loss combined with this distribution that you see on the left. And the main takeaway, and what I will dive into for the next few slides, is that the combination of those two things is actually something you need to be very cautious about. And in fact, if you think about it at a very high level, and as we will see later, you can easily see that trying to solve a classification task with such imbalance is going to be prone to some instabilities. And in fact, to make things even worse, depending on how you regularize and how much you regularize your model, you will actually make this mixture even more unstable. So that's really the entire point of this study, which is that you deal with very imbalanced classification task, and you have some regularizers that you use during training, and all of those things do not mix well to produce a nice model at the end. So let's try to pinpoint a little bit more what we mean by explosive mixture in general. So let's first consider this next token prediction setting. So this is the training loss that we employ. So this is exactly what I mentioned before, but just now put into this equation. So you see you have your model prediction f theta. You observe tokens up until some time t or position t, and then you try to predict the next one with this cross-entropy loss, and you do this over all the steps in your prompt and then all your prompts. So this is just a very typical next token cross-entropy classification loss. And then we have this extra regularizer here, which is weight decay parameter or Tikhonov regularization on the LLM weights, basically. So this is the setting that we're going to use, which is, again, the very, very typical one. And in practice, we are going to use IMDb, so those examples I showed before, so those movie reviews. And we have two variations of this. We have, let's say, a small version and a larger version, which we call IMDb and IMDb XL. And in terms of actual LLM architecture, we are going to consider 4 of them. So there is this OpenLM1 and the Qwen2 models. And for each of those families, we are going to consider small and I will not dare to say large, but at least medium scale model. So we see from a few million, few 100 million parameters to a few billion parameters. And this will be useful to try to understand that our findings are not specific to small model or specific model families. So hopefully this whole setting makes sense, and yeah, feel free to also interrupt me if anything seems confusing in those. So given this specific setting, what we propose to do is just to solve the usual language modeling or next token prediction task and see what happens in terms of loss, per token loss, as we vary this lambda parameter here, so the strength of the regularizer that you use. So I will go very carefully into each of the findings, but just to give you first a very broad picture, this is a type of result that we obtain. So for each dataset version, so IMDb and IMDb XL, and then for each architecture family and size, we will repeat the pre-training with different strengths of weight decay. And then we are going to see what is the per token cross-entropy loss, which is based if we look at low frequency token in blue or high frequency token. So the goal really is to understand what happens in terms of training dynamics as you look at those high frequency tokens, so the ones that are present with very high frequency in your dataset, and the ones that are only present a few times in your dataset. So just going back to make this very clear, so if you remember this distribution here, we want to compare what happened for those tokens that are here, and then those tokens that are here. So hopefully this is clear, and yeah, let me know if there is any question. So this is the whole set of experiments we are looking at. And from this, we obtain a few very interesting findings. So let's go into them one by one. The first one is that as you increase weight decay, so we start from 0, no regularization, up to 1. So as you increase the weight decay, you always have a disparate impact on the low frequency token. So what this means in practice is that taking again those experimental findings we had before, if we look at increase in lambda, so increase in the weight decay, and we see how the loss evolves on both the low and high frequency tokens, you see that those orange ones, so the high frequency one, the distribution of the loss over those tokens is pretty much the same. So it does not vary at all. So here you see, for example, a zoomed version. So the difference between those orange guys here is negligible, or at least by eye, you cannot see any difference. And any statistical test will also see that, yeah, those are pretty much the same distributions. So as you slowly increase the weight decay, the high frequency tokens don't see any difference in their actual cross-entropy loss. Of course, if you start increasing the weight decay beyond what people would call reasonable parameter, you can start impacting those tokens, but this is really very aggressive weight decay. So in practice, we are more interested in this part of the figure. So high frequency tokens are not impacted as you start increasing the weight decay, but low frequency tokens are very, very much impacted. So you see, if you go, for example, from this left case here, which is 0 weight decay, to this case here, which is a weight decay of 0.2, so very realistic setting, you can see that you have a big shift in the distribution of the losses for those tokens. And this discrepancy in how much weight decay impacts the distribution of the high and low frequency token losses is true across the different dataset size and across the different LLM architecture as well. So you can see this is the same for this setting here. The high frequency tokens are not impacted and the low frequency tokens are impacted. So this first finding seems to hold across all those experimental settings. The second one is that when you change the architecture, again, you also impact the low frequency token more aggressively than the high frequency token. So if we take again this figure that you saw before, and now for a moment, let's just fix a weight decay we want to look at. So for example, around 0 or 0.1. Then what you see is that if you look at the high frequency token and the distribution of losses that you have, roughly between the different architectures, you have the same type of distribution. So for example, if you go here from a small OpenELM model to a larger OpenELM model, this distribution here, this orange one, is pretty much the same in both cases. But if you look at the low frequency token, so those blue areas here, you see there is a big difference between using a small and a large model. And this is true here for IMDb. This is also true here for the IMDb XL. And so what this means is that when everything else is kept the same and you change the architecture, you will have a very, very disparate impact on those low frequency tokens. And you see the difference is very, very significant here for those low frequency one. So that's really another important finding. And this is true for any value of lambda that you will use. So if you say, okay, for lambda 0, you see this discrepancy. For lambda 0.1, you see the discrepancy again. So this is true almost for any practical strength of weight decay. So this is another important issue that you obtain. And then another one, which is even more important for like pre-training strategies, is that low frequency tokens are always learned last. So to try to convey this, we don't look anymore at this cross entropy loss on the y-axis, but now we look at the speed of learning tokens. And the way we measure that is if you think of the per token evolution of the training loss, you can basically compute the area under that curve, and you can see that if you have a very quick training, then you will decrease very rapidly and then plateau pretty much at 0. So there is a small area under. And if the training is slow, you will have a much more linear trend or even less than linear. And so this area under the curve is a good proxy for this training speed. So we derive this, what we call token speed, as a reparametrization of this area under the curve of the per token training loss. And so this is a proxy to measure how quickly you learn a token versus another. And so what you see here on the x-axis now is no longer the strength of the weight decay, is the percentage of token per bins, you can see here. And we compare small versus aggressive weight decay. So what you see is that depending of how much regularization you put, you can actually slow down the convergence of the low frequency token. So if you are here on the right, you see that there is no difference with or without aggressive weight decay. But on the left here, you see there is a big discrepancy in how fast you learn those tokens. And again, this is extremely important because if you think in practice, ideally you want to learn all tokens equally fast, right? You don't want to change a little bit the weight decay and suddenly some tokens are going to be learned very slowly, which means that you need to increase the length of your pre-training. But in practice, this is what actually happens behind the scenes. So this is something that is very important. And again, here you measure this by comparing the per token speed. And this is true for different architectures and datasets as well. So you see that you always have slower dynamics for the low frequency token than the high frequency token. And this is exacerbated by using aggressive regularization. And again, here this is measured as a function of the strength of weight decay. But as you know from other studies, things like size of the mini batch and the way you do optimization are proxies for regularization, which probably will have the same effect as well. So that's something that's very important to look at. And you will only be able to see those changes by looking at per token statistics, basically. So in practice, of course, you might say, so this is quite interesting. We have this trend that is different with high frequency and low frequency token. But in practice, you may wonder, do we even really need to learn those low frequency token? Because you may think, okay, those are very odd things in the text maybe, and okay, maybe even if we don't learn it quickly, it's not a big issue in practice. But it turns out that if you take any prompt, so here is an example from this IMDb dataset again, and then you see which part of that prompt is related to the high and low frequency token, you obtain this coloring. So in blue, you have the low frequency one, and in orange, you have the high frequency one. And so what you see is that in practice, for the model to really understand what the prompt is about and to be able to do all sorts of question answering from that prompt, you actually care a lot about those low frequency tokens, because first of all, you notice that all the numbers are in those low frequency token. So of course, it's very important to capture them, because if you are given this prompt and then you're asking a question to retrieve those numbers, you need to be able to encode them accurately. But also anything that is more about understanding and reasoning is also related to those low frequency tokens. So you can really think of high frequency as a almost blank or boring punctuation characters that, of course, is good to capture, but they are not the tokens that will really help you to do better reasoning or better question answering. So the whole point of this is to say, really, this low versus high frequency token comparison matters a lot, because the low frequency tokens are the ones that you want your model to really capture and practice. So this is really an important thing to keep in mind. So as a last maybe motivation for those findings, you might think, okay, this is nice. You show some trends as a function of weight decay, for example, but how is that actually relevant to practical pre-training that is done at industry scale? And so, of course, you can try to see, okay, what pre-training recipes people have been using for very large-scale models. And not all of them are public, as you can imagine, but you can still find some studies that try to describe them. And all of them that you will find that are open source or published actually use very aggressive weight decay. So here, for example, you see this OpenElm papers, which is one of the architecture we used. They use a weight decay of 0.1. You also have studies that justify you need weight decay to do pre-training just for training stabilities. So you cannot move away from it pretty much, which means that all the current LLM pre-training use aggressive weight decay. The first Llama model, for example, you can find the training recipe. Again, you use a weight decay of 0.1. And even if you look at things, for example, there is a very thorough Hugging Face huge summary for guidelines on how to build a LLM from scratch. And they will specifically say that you need to do regularization, and they will mention L1, L2 regularization, L2, which is the weight decay. And again, our findings probably extend beyond weight decay. So really, this is a prominent part of current pre-training strategies. And in fact, if you look at PyTorch, for example, they go as far as to put quite aggressive weight decay as a default parameter for this AdamW optimizer. So it's something that really is present throughout optimization landscape nowadays, and therefore also in a pre-training setting. So it's really a practical setting that we looked at. And so the main point of those findings is really that you should look at per token training dynamics, and you should try to move away from just looking at aggregated statistics like your average loss or average prediction performance. You need to go beyond that to understand what are those trends, because those could open the door to many developments for LLMs here specifically, but in general, other systems as well. So if you come from maybe more applied things, you might think, even from the first slide where I mentioned this imbalanced token distribution and this cross-entropy loss, that yes, this will be prone to create some problem. And that's true. If you Google a little bit around, you will find very easily a lot of research studies that try to basically correct or give guidelines on how to do classification with very imbalanced data or imbalanced class distribution. So this is obviously not a new problem on its own, but it's a problem that is persistent throughout LLM pre-training, and which may be inherent to just the way language is formed. If you know about the zip flow and the way linguists model language, you have this exponential distribution almost by construction. And so this opens some new interesting problem as to, is next token as a classification problem really the best way to do pre-training? Because inherently, by construction, you will be in a imbalance setting. So this is quite interesting, and maybe there could be ways to explore those previous studies to try to come up with better solutions. Next, what we did in the study is to actually try to understand this a bit from first principles and try to see if we could prove why this is the case. And again, because we are in this very nice classification setting, we can actually reuse a lot of known theory to try to understand that this discrepancy that we observed empirically is to be expected and in fact can be proved. So for this, we need to introduce a couple of notations, but hopefully nothing too crazy. So we define the vocabulary size as V and the total number of sample as N. And then the only thing that we need to be careful about is how we denote prompt. So we will denote it by xki when this is a prompt whose next token to predict is k. So you can really think of this as grouping the prompts based on which class they belong to, i.e. which token is to be predicted from that prompt. So xki is basically the highest prompt among the ones that needs to predict k as the next token. So hopefully this grouping makes sense. And then we will denote that by nk, the number of prompts we try to predict k with k as the next token. So the total number of prompt is obviously n1 plus n2 until plus nv, basically. So this is just a grouping so that you can see you have a per class grouping of your entire data set, which is shown here. And this is just a slight way to factor the full data set so that the theory becomes very easy to derive. And then we will denote by H the representation of the prompt after you feed it through the LLM. The only assumption we have is that this is non-negative, but this is quite realistic because in practice, you will use ReLU or swish as activation function. So we just assume that the d-dimensional vector output of the LLM is non-negative. And then we'll denote by W the last layer classification head, which is the one that, given this representation, tries to predict what is the next token, so the target of the classification task. So the loss looks like this. Again, pretty much the same as before. We just abstracted away f theta of x. Now it's directly this representation h. We have this linear classification head, this target here, which is just like the one odd version of the token k. And then we have those regularizer, Tikhonov or weight decay regularizer, both on the classification head and on the representation h. So again, this non-negativity assumption on h, and then we say we use a non-zero weight decay. So if you put yourself in this setting, which again is exactly the same as the one we talked before, This is actually something that's very known and has been studied before, and you can, from this, obtain a few key properties of what the optimal representation looks like. So we have those key findings. Not all of them are really important for us, they are just here for completeness, but just to give you some intuition, the first one is that you have a within class feature collapse, which says for whatever prompt which has a same token as prediction, those representation will become close to each other, which makes sense. Then you have those representation per class that become orthogonal to each other for the ones that try to predict different tokens. So basically, you try to predict different tokens, your representation will be different from each other, which again is pretty intuitive. But then what is more interesting to us are those ones, and especially this one that tells you what is the norm of the representation of the prompts that have to predict K as the next token. So you have this expression here, which involves this constant, this per token constant MK, which is given by this formula. So the bracket and this diamond, you can just think of this as a ReLU activation function. It just says if its input is negative, this is 0. So all of those derivations are actually very insightful because you can find sufficient and like a probable condition under which the representation of the prompt that try to predict token K will actually become null or with 0 norm, i.e. you will just disregard that token from training in your LLM. And basically you can show that as soon as NK, so remember NK is the number of prompts that tries to predict K as the next token, as soon as this frequency is smaller than this quantity, then you will just disregard those prompts or this like next token task from your representation. So this is really nice because this explains and gives some intuition in the relation between the per token frequency, the total number of samples you have in your dataset, and the regularization strength you apply on both the classifier head and the representation. So you can see all the interaction between those things will make your model and your representation completely disregard some of the token for the prediction task. And so what this means really is that you can prove and justify those empirical findings we had from this theory, and you can understand all those hyperparameters like weight decay interact with the full dataset size and the per token frequency and what is the impact on each of them. So here we only looked at the actual per token representation, but the same formulation can be used to also justify and probably describe this training speed that we spoke about before, that low frequency tokens are learned at a slower rate, and this rate is even slowed down more as you increase the strength of the regularization. So the point is that this is not just something we can observe, it's something we can prove, characterize, and from this try to derive a better solution. So from this, those are most of our findings. So there are a lot more ablations and details in the paper. But before concluding, I just want to mention that the solution to this problem may not be as trivial as, for example, making tokens with a balance or uniform distribution. So to justify this, which again is not verified in LLM, but has been verified before, I want to bring out a previous study that we've been doing in the context of computer vision. So in this paper, we looked at ImageNet, so a small change of regime, but in that case, you have natural images, 1,000 classes, and the classes are pretty balanced. Basically, you have the same number of images among each of the classes, up to like plus 10, 20% variation, but it's close enough to be considered a balanced classification task. And in this paper, what we found is that although you start from this a priori very nice, well-behaved dataset with balanced classes, you can actually see that as you increase the strength of the weight decay on the x-axis here, as the impact on the per class performance may vary a lot depending on which classes you look at. So for example, you can see here, you have the average test accuracy on ImageNet in blue. This is with a ResNet 50 backbone. And you see that as you increase weight decay, eventually one class will become very well predicted by the model, and one will become near random accuracy, basically. And so this means that there is something a bit more fundamental about this whole problem than just balance of the token. There is really a case where we start from a mindset that as you increase the regularization, which is a way to control the model complexity, as you will obtain the best test accuracy. And we think that this best test accuracy is also going to coincide with the best per class test accuracy. So this ideal picture that you can see in many notebooks. But in practice, with and without class imbalance, it seems that we are more in a regime like this, where when you control the model complexity through regularization, as your optimal on average is actually not agreeing with the per class optimal value. And this is really important problem where the architecture, the dataset, the optimizer all intertwine to lead to this case. And so the main point here is just to say that even if we just fix the tokenizer, this could not be necessarily the end of this problem. And so really the key moving forward is to have more monitoring, fine-grained monitoring, to really understand all those issues and how to improve them, basically. So just to finish on that note, I just want to mention a couple of interesting research questions that stem from those findings. The first one is obviously, can we develop better pre-training objectives? Because you could try to argue that if you scale beyond the settings that we look at the papers, this problem will go away. But it turns out that at least in other settings, for example, with vision language, we found that some properties or some issues of those models actually do not go away just by scaling, but playing with the pre-training objective is really what will give you a better representation. So it will be very interesting to think of this problem are very relevant, not just for academic setting, but really industry scale pre-training, and see if we can have better pre-training objective, which again, probably is not going to be as simple as just having a better tokenizer. Another thing is try to understand if this type of discrepancy that we had with high and low frequency token is really specific to this decoder only architecture and pre-training regime, or is it also true for things like BERT style pre-training, which a priori, given this previous study I showed on ImageNet, is hinting at the fact that the same problem will be for BERT. Maybe it will not be on the same token or with the same strength, but it seems that there will still be some biases coming from the architecture that will impact some prompt or some token more aggressively as a function of the weight decay, but this will be very nice to verify. And then can we reconcile regularization with fair token training dynamics? And this is a very important question. So here we speak about token within a LLM setting, but in general, per class training dynamics, which is an open, fully open problem that is really underexplored at this point. And all of this, again, from a very practical point of view, is not just to have better per token losses, but you can really think of this as a way to also make pre-training much more efficient. So if you go back to this training speed that I showed before, where low frequency tokens are learned very slowly, you can think of motivation for practitioners, which is just to say, if I can speed up the training or the learning of those low frequency token, maybe I can reduce by half the pre-training time. And so although I don't really mind in fine about this per token training dynamics, I do mind about reducing my pre-training time, and this could be one way to do it. So again, the motivation for this goes way beyond sort of a high-level token fairness issue. It's really about understanding better what you learn, how you learn it, to then have more practical pre-training solutions. And yeah, so with that, thank you again for the invitation. I'm happy to take any question now. But if you don't have time to ask questions or you want to dive into things deeper, you should definitely feel free to email us, and we'll be happy to answer you to pretty much anything. So thanks.
You can unmute and ask.
Yeah. Hi, Randall. Can you hear me?
Yeah.
Yeah. So yeah, I was discussing with Imtiaz about your work. So like we're chatting about like what is going on here. So like I had one question. Like so you in this work is about mostly pre-training, and but the practical models they goes through like multiple stages. Like they have DPO, safety, etc. So I'm interested in knowing like how this actually manifests after those steps, because like recently I worked in ag, and like there are problems with hallucinations even with the instruction tuned and other models. So yeah, so that is the question.
Yeah, that's a very good question. In fact, that's one thing I probably should add in the open research question as well. So as you said, in practice, if you are an end user, you probably don't really mind about this pre-training phase because there is maybe nothing you can do about it, but you want to know what happens in this phase here. And this is also an open question. So if you use, for example, LoRa fine-tuning, let's try to quantify how much of this issue can be corrected or could be actually amplified when you do this sort of LoRa fine-tuning? And is there a way to correct those pre-trained models just from a few LoRa modules? So this is an open question that is very interesting. Try to see, can we do something at this stage here to correct that bias? Or at least see what happens. Do you keep the same bias? Do you increase it? Because again, the mention I had before that pre-training can be sped up if you understand those per token training dynamics, could also be true for fine-tuning as well. Maybe when you do LoRa fine-tuning on your new text corpus, you also adapt much more slowly on some tokens, and finding a way to resolve this issue could make LoRa fine-tuning much faster. So yeah, that's a really good question, and at this point we don't have answer, but that would be very nice to look at it as future work. Yeah.
Thanks.
Okay, so can I ask?
Yeah.
So you mentioned that you don't think that simply balancing the low frequency tokens with the high frequency tokens because of the work you've done in computer vision.
Yeah,
so my question is like, is it somehow like a fair comparison to compare like computer vision with NLP, considering the tokenization or the encoding step is really different? So for instance, in computer vision, if you're balancing classes, I mean, is a class really just as fine-grained as tokenization in NLP? So like you're not balancing the features within the classes, right? It's like there are more fine-grained features. So it's like, is it somehow a fair comparison?
Yeah, that's a great question. So first, as you said, computer vision is a bit more complicated also because when you speak about one class, you can have co-occurrence of objects, you have many things happening in an image. So you have all those dynamics that are much more complicated than when you are in a token space. So for sure, it will not be a one-to-one comparison. But with that being said, it is known that if you just think about having a classification problem, depending on the architecture you have, you will have different type of biases into what feature you capture in your data. And so, for example, with LLM setting, you could think of changing, for example, the number of attention head or layers could make your model learn fast or slow dynamics in your sequence of token with more or less ease. And this sort of implicit bias can be exacerbated by regularization, and this could impact the per token accuracy as well. So although I don't think, as you said, it's as simple as this one-to-one comparison between computer vision and text, we know that there is a lot of implicit biases from the architecture that are true regardless of the setting you are in, and those will have a strong impact on per token performances. So the analysis should be LLM specific, but I still believe that even with balanced token, there will be discrepancies between some tokens just because of the actual nature of the dynamic of those sequences. But this will be interesting to look at more in depth and quantify precisely. Yeah.
Thanks.
If you don't have any other question, we can conclude the session here. Thank you so much for your time, Randall. It's really
Of course. Thanks for inviting me. Have a good day.
Yeah, take care. Bye.
Thanks. Bye.